Welcome. Next, I want to support getting information about a value even if you have no idea of the type. And the way I want that to work is basically, if you have a generic function, hang on, let me share my screen. Let's say you have some function foo that it accepts a value of type t, or a list of t or something. Basically, you have a value in a generic function and you don't know anything about the type, which means that you can't do anything with the value. You can't access a field, for example, a field bar, because that won't work with all values. You can't switch on that if it's an enum. And I do want, for example, if you want to debug print a value, I think it's still useful to be able to do something with a value. And I think the way I want that to work is to have a built-in function, to anything, basically. That is like a compiler provided function that works on any value, and it returns you like a first class representation of that value. Let's maybe prototype that in the standard library. So I want a new file like anything, and this should define a function to anything that just accepts a t, a value of t, and it returns anything. Now, what is anything? Now, anything is a type that can represent any value. So let's maybe look at the type. These are all the types that Plum supports. And if that's a byte, then this should just contain immediately the byte in there. If this is an int, then it should just contain the int. If it's a type, then it shouldn't contain any runtime information. Yeah, because you can't do anything with types at runtime. If it's an array, then it should actually just contain, an array of anything values. A never type can never be constructed, so there can never be a value of that type. If it's a struct, then it contains an array of names and values of these fields, and the values again are anything. If it's an enum, then it doesn't list all the variants, but only one variant, so it only has a single name and value. And if it's a lambda, oh, that is difficult. Let's not have anything in there for now. And recursive types don't need to be modeled in here. All right, so for example, let's say you have, the type, we have the type linked list somewhere here. Let's maybe copy this. Let's say you have an instance of this type. First of all, linked list is defined as an enum that is either empty or it's more, and if it's more, then it contains this struct here. Like this enum, you could also write that as this. It's one of these two cases. If it's more, then it contains an item of that type t, and the rest, which will be kind of recursively a linked list, which is then either empty or more. An instance of a linked list might be this. It might be more of an item 5, and the rest being empty, for example. And what I want to be able to do is write a function that works, debug-print, that can debug-print any value into a string by calling the value to anything. And if that value is this linked list, for example, then it should just be able to anything. It should basically contain, return a representation of this. It should return anything.enum with the name more, and the value being a struct with an array with two fields, like a struct with two fields, with the item field, which will be anything, this int, and the rest will be again an enum with the name empty. And by having this kind of first class representation, you can then iterate over the struct fields, for example, and convert those to strings. And you can kind of, you look at the enum value, you have all the structure of the type, you have that available as first class information. Which means that the memory layout of this anything is way less efficient than the memory layout of this linked list. Because here, like, we really store the strings of the individual struct fields, for example. In here, we just decide on a memory layout at compile time. But having this first class representation of values that you can inspect at runtime, I think that allows you some really cool things, like, for example, debug printing, but maybe later on also some way of, I don't know, passing some JSON into a target type T, and that returns you a T, something like this. If we have a compiler provided way of converting any value to this, kind of anything representation, and converting a given anything representation to a concrete type that we already know, that we want to get out of that, then we have, we still have the property that the type level, that the value level, that control flow can never influence the type level, unlike in Zig, for example, with comp time. Control flow can never affect the types, which means we can have great tooling, we can have type inference, we can, have generics in the code without passing around first-class types all over the place. But we can have function overloading. Like, these are all benefits that we get if we don't allow arbitrary compile time execution for determining types like Zig does. But we still get a lot of the benefits that some languages like Zig have. Not all of the benefits, but at least for kind of reflecting over types and having type information and value information available during the runtime of the program. Writing code that is generic over any type and then it does something with that type. We still have that that way, that possibility. All right, so I basically want to have a toAnything function that takes the value and returns anything, but I also want basically be able to, if you have an anything, then you should be able to do two, point or linked list of int, something like that. So I also want a to function that accepts an anything and a concrete type that we already know that we want to get out of that, and it should just return you a T and just crash if the anything doesn't match the type. So if you pass in anything int, but you want to get a point out of there with like x and y coordinates, a struct, then that should just crash. Which means that when calling this to function, you basically need to ensure that the anything has the correct type. All right. Yeah, enough explaining. Let's maybe build, flesh out the rest of this module. How do built-ins work again? We have this built-ins module, and then in there are a couple of types and functions. And I think I basically want to have a function, value to anything, maybe, that takes a T. And I want anything to value that takes an anything and a type, a T of some type. All right, and then these here would just call the built-in functions. So to anything on a value actually calls value to anything on that value, and to a type returns anything to value using that anything and the T. All right, yeah, we'll build that later on, I guess. And this one as well. And maybe have a format function that, right, we can already create the format function. Formatting anything into a string. That would just switch on that. And if it's a specific byte, then we just return byte.format, I guess. If it's a specific int, then we just return int.format. If it's a type, then we don't have any runtime information, so we'll just do type. I think I'll use lowercase for most of these, lowercase for, because we are on the value layer. If it's an array of items, I would actually, I think we want something like this, lowercase array, and then in here the items. So let's use this syntax, with the dot syntax. Okay, so converting the items to strings. Ooh, items is what exactly? Items is an array. Okay, so I think we should be able to iterate on that and then map the individual fields using a lambda that we can create like this. So given an item, which will be anything, we then want to do item.format. And then in the end, we'll join those using a space character. Nice. Okay, then struct. If this is a struct with fields, we'll actually do something similar to this, except we'll print an ampersand and then we'll iterate over the fields. And given a field of the type, struct with, what was it, name and value, we actually want to format that something like this. So we want to have the name plus a colon plus the formatted value. So like this. And for an enum, oh hang on, for an enum things are actually a bit easier. Because this right here is, you can directly pattern match that, or pattern destructure that. It has a name and a value, and we'll just want to do name. Oh hang on, no, we want to do pipe. Yeah, then the name, then colon, and then the formatted value, and then a closing parenthesis. Beautiful. Yeah, and lambda, I don't know. I'm not entirely sure how to handle lambdas at this point, but yeah, this, I may have to change that later on. That's fine. So in here, let's import anything. And we'll need the type anything, and then these basically. So any t can be converted to anything, and an anything can be converted to a t. Kind of mind-bending, but sure. Yeah, we'll probably need to import a lot of other stuff as well, like strings and ints and so on, and bytes. So let's see, byte and int and string. All right. Oh yeah, also arrays. And of course iterate over an array, and we are formatting bytes. So format of byte, format of int. Okay, these are these. Oh, plus functions for strings, map for iterators, and join. Yeah, a lot of stuff. Let's see, plus for strings, then iterator. We'll need the iterator function so that we can then import the map function of an iterator of A, and a lambda that takes an A and produces a B, and also the join function on iterator of string and a string. Okay, that should be enough to compile that and that. Yeah. Cool. Let's try to compile that and see what goes wrong. Okay, so in the main function, I just want to do, let's say I have some point with x and y, and I do to anything dot format. You know, and yeah, we'll import anything, we'll import to anything that takes a t, and we'll import format of anything. Oh yeah, that is also something that anything exports. Okay, yeah, right. In here we also need types. That was quite easy. Yeah, true. And here for the individual fields, this would be field name and field.value.format. Yeah, we can't use destructuring for lambda parameters. I might actually add that at some point, but I'm not entirely sure about that yet. So, okay, some function is imported incorrectly, apparently. Yeah, anything to value. Okay, so function built-ins dot anything to value doesn't exist. That is to be expected, actually. So now we'll need to add those built-ins. Those two built-ins, value to anything and anything to value. And let's start at the beginning of the compiler pipeline, the bacon. Yeah, we don't need to do anything there. In the abstract syntax tree, the toast, we also don't need to do anything. And the next function, the egg, yeah, here we need those because here functions are resolved, which means that those built-ins need to, the compiler needs to know about them in some way. Oh, look at that, a list of built-ins. Yeah, type operations, let's also do like anything operations. So we'll have, what was it, value to anything and anything to value. Beautiful. All right. Yeah, we'll also add them here. So egg built-in dot value to anything and anything to value. Yeah, which means in this lookup, wherever that is, we'll need to handle that at some point. Oh yeah, getting the signature, like not the name, but the type signature of that built-in. Yeah, so value to anything really has, that has, the arguments are basically any, any t, and it returns anything. That's probably not a thing, so let's add the builder for that. Types, builder, type. Yeah, type info is here, and we also have type anything, which will be quite similar actually. So the type anything is an enum with a byte that maps to a type byte, with an int that maps to an int, with a type that maps to nothing, with an array that maps to, well, an array of recursive types 2 up, let's see. 1 up would be the array itself, 2 up would be more anything types. Yeah, never doesn't exist. We have structs where the individual things have a name and a value, which is this one. We have an enum, which is not an array, but just a struct with a name and a value, like so. Yeah, lambda doesn't have any information here, so this is type nothing, and recursive doesn't exist. And this type anything is being returned from that. Yeah, and then we have anything to value that accepts an anything, and a type actually. Ooh, how does that work? Like a first class type, basically. Type, I guess. And it returns a t, so type t. It is worrying that we don't have a name for that one. Yeah, this is not enough information, actually. Nah, I don't like that. I mean, I know that let's add it to do it here. Link type argument and t somehow. Yeah, imports and exports and the substitution stack, especially for built-ins, are a bit of a mess. I don't quite know how to fix that. In some future video. Okay, so yeah, we do handle those now. The error is just stale. So let's try to compile that, see what else is missing. Okay, egg to yogurt. In here. Oh, hang on. So compiling to egg apparently works. Just, going further doesn't work. All right. This does, well. Let's see. Case. Oh, hang on. This should just be as easy as that, right? Well, something like that. Push type. Yeah. Okay. So we do have value to anything. So for the first argument, the substitutions, whatever that is, we'll specialize that and we compile that. That's the type. And now we basically need to push a call to some sort of conversion function and then return that. Okay, so here we have cast. And similar to casts, we now want to do kind of conversion from a typed value to this anything value and anything value to that typed value. I think type info is also defined in here. Yeah, push type info. Yeah. I think I'll add some sort of anything code. Not sure what exactly that's going to be, but so similar to casts, we want to generate functions for these anything conversions. So compile value to anything fun. The signature is going to be, well, hang on. At the position where we call, yeah, here we want to call that function. Rather than doing that, we'll just do push call some function. And let's get heavily inspired by this one. Yeah, we don't have any special casing. Oops, any special casing there. We just have this convert fun, and that's going to be compile value to anything fun of the type. Something like that. Yeah, and then we just call that function with the argument hang on. I think it's even easier than that. Yeah, this basically just, we just want to do that. Yeah, the type is just that. It's already been specialized and compiled and so on. All right. Now the casts, they work on egg types. You see, that is kind of not sure what to do about that. I think that we do want, what's different about the yoga types? And we don't have any sort of, like, these are specialized types, I think. And do we have, I think we no longer have lambdas and stuff like that. So we do want the egg type actually, which means, well, this is actually going to be that. I think. Yeah. 40% certain this is correct. Oh, hang on, and this should probably go in there. So we call the convert function, which is that one. We call that with our value, and that is supposed to result in the argument. Oh, no, that is supposed to result in type anything, right? Right? Not totally sure about that. Let's just see what happens. So if I compile value to anything function, it has a type, which will be an ACK type and a context, and it just returns the signature of this compilation function. So we cannot canonicalize the type. Okay. And then we say, type to anything. Alright, and then we have this compile cast fun body. I think we're going to replace that with compile value to anything fun body with the type and the param and the context. Alright. Compile value to anything fun body with a type and a couple of other stuff. And let's just panic here, maybe. With the type. Yeah. Let's comment out this switch and just see what happens. Well, true. All right. In this mod, we do import the new anything.mar part. Yeah. Oh. This does need an egg type. So I think just don't want to do that. Push call fun. Yeah, with bodybuilder, that, and then this is supposed to be the anything type compiled. All right, that compiles at least. Now let's see what kind of type it figures out. Oh, okay, yeah. So what is in the map? Yeah, basically this didn't work. Hang on, this one. Subs are the substitutions. Let's just print them like that. This is taking a long time, the compilation. It's a bit unfortunate. Okay, it maps T to T. Do not like that. T to T. Can we do this sort of thing? You're getting the type of the first argument. Yeah, that seems to work, although I think we can do like a certain closure, something like that, to convert that back into an egg type. Hang on, also, oh, I see. So this T is T. That is not a great substitution for this type. I don't quite get that. Okay. Well, anyways, I think we'll just do that. Yeah. To make more beautiful after figuring out how type substitutions propagate through imports. Yeah, I think imports and exports are kind of the next, basically the only remaining big construction side in this language that's not, where I don't really have a solid plan or idea, where I still need to figure something out. All right, so we have compile value to anything fun body, and this is the type that we want to convert to anything. All right, I'm not going to do that right now. I'm going to take a break, and then afterwards we'll see. All right, so I'm compiling the anything body. Let's look at that. Yeah, I guess that depends on the concrete type that we use. So we have to extend the type one level, and then we will switch on that. If it's a primitive type, like that, then we switch on the name. So if the primitive name is int, then we're going to do something that will actually just result in, well, an anything push enum, something like that. Let's actually look at that. Yeah, we can push an enum with a name and a value and then a type. So the name obviously is going to be int. The value is going to be an empty struct. So that would be body.push nothing. And the type is, well, type anything dot compile. And we're basically doing that with all the variants. So let's actually see, we're basically constructing this enum here. You know, if the value that we have is a byte, then, oh, hang on. As a payload, these need the actual content. That actually makes sense. So for an int, the payload will be the value. Yeah. And for byte, the payload will be the value, which will be a byte. If it's an array, then we're gonna do something. Still need to figure that out. Array to anything. For now, I'm just going to remove all that. Yeah, and otherwise we say, turning, like, and this is an unknown primitive type, basically. Shall we get the type? Yeah. All right. I like that. Then let's extract the name ones and then simplify these. All right. Oh, hang on. We could even put them on the same line. Kind of. Yeah, this is clean. All right. Then, if we have a struct, well, we need to create an array an array of structs with a name and a value. Right, so for every field, we basically, well, we have the key and we have the type, which is just the value. This is already canonicalized because extend one level results in canonicalized types. Alright, and what we do is we want to, in the end, push a struct, which probably needs a map. Oh, hang on. Let's rename that to like anything fields, and then in the end we have these fields, and hang on, what do we have? The type is well, the type is difficult. There was another builder in types in here. Type anything. Yeah, the type is basically this, but this is recursive to the anything above, so yeah, I guess the type will be a struct. Yeah, indeed, this is a struct. This is just a map with name and value. I see, that makes sense. So the name is going to be the field name, actually. And the value is going to be body.push. We have this nice push cast for casts, and internally that compiles a cast function. I think we want something similar for anything. So, some sort of push to anything given a value and an egg type. Yeah, and then that just compiles a value to anything fun with the type and the context. And then we call that with the value. And that results in the type anything. Yep. Well, that means that down here we can just do actually we want to convert the field value, which is hang on. Oh, I see. Yeah, let's actually split that into multiple parts, I guess. Yeah. So the field value is going to be well, this basically. Push member with the value and the name that we have plus the field type. And then the field value converted to anything would be body.push to anything. Oh yeah, of that field value with the type field type, like that, just like that. And then in here we just use the field anything value. Beautiful. And that is a struct that contains a name, which is a string, and a value, which is an anything. Basically this. Although that is not canonicalized because I mean this is recursive 2 levels up here, that makes sense. This one though, this struct containing a map with name and value, that could just be replaced with that. Yeah. And same here with that entire thing. Like that. Recursive 2 would be 1, 2. Enum contains a struct with name and value. Yeah. Alright. Okay, so that's the struct. And those are just the individual struct fields. Now we need to put all of them into an array. So that would be body.push array, I guess. And let's actually turn that into a list of IDs. Like so. And then we push an array. That takes items. And then the type, which is the type of the array itself. For some reason. Alright. So this needs items. That would just be, well, anything fields dot to slice. And then the type of the array itself. Which would be an array of that. Oh man. Now, of course, again, this is not canonicalized anymore, because we can simplify these. Instead of going recursive up only 2 layers, you know, 1, 2. Oh, hang on, that's actually correct. Yeah, it's just that this one goes up recursive 3 layers, 1, 2, and 3 to the struct, and then wraps that in an array, so we can just move that in there. And the enum only wants to move up 2 layers, that's still fine. Yeah. Alright. Yeah, those are the anything fields now, this array, and then we push an enum that needed a name, yeah, and then a value and a type. The name is going to be struct, the value is the anything fields, and the type is going to be type anything, compile. Oh, I think these also still need to be compiled. Oh man. Alright. What's going on here? Oh, this needs the context. Sure. So we don't try to recursively compile functions for recursive types. What's going on here? String, string, and string ID. I see. So this should really be body.push string. And that's maybe, I don't know, that still fits on a single line. Nice. Alright, then we push an enum. Perfect. Now we push an enum for the struct. Alright. Now comes the enum. Now let's kind of review this. We access the struct member of our original value. All the individual fields, we add them and we access them, and then we convert each of those into an anything value. Then we create these structs with name and value of those anything values. We put those in an array and we wrap that in a struct enum variant. Let's see. We have a struct of some fields. So we take the individual struct fields, turn those into anything, put that into a struct with a name and a value, put those in an array, construct the enum variant struct. Alright. For an enum, what we need to do is we basically need to create a serialized version of the enum variant and then a serialized version of the value. So I think we need to switch on the enum. Yeah. Yeah, each branch is just gonna result in a different name and value and struct. Okay, so we have cases that already make sense. So then here we have the variant types. They have a name, they have a type, and then we build a body, which is going to be a case body, sure. And then we have a value. Yeah, that makes sense. Pushing a parameter of the variant type. All right. So we have the payload basically of the enum. We want to convert that to like payload value, payload anything. And that is the case body dot push to anything on that value. And the type is going to be variant type. Clean. And then we put those into a struct. With a name, which is going to be the case body. The name and a value, which is going to be payload anything. And the type of that is going to be pretty much this, actually. It has a name, it has a value, which is a type. Yep. Should I maybe add those in here? Type anything field, something like that. And that is that. Yeah, and then let's also have type anything fields plural, which will be an array of types. Nice. I like that. I really do like that. So this will be type anything fields.compile. And this up here will be anything, type anything field to compile. Alright, yeah, and in here this will also just be type anything field dot compile. Nice, but rather like variant compile. Which just happens to be the same, you know. All right. Yeah, that's basically a struct containing the name and the value. And then we put that into the case body. All right. Yeah. And then in the parent body, finally, we have a switch from the value with cases, and this should result in the type, type anything variant. Yeah, name and value, like so. And then what we want to do is, well, we now build this by switching on the original enum and, depending on what variant it is, constructing the correct string and converting the value that the payload to an anything. And now we want to create the surrounding enum variant for that. So that is just body push enum enum with name and value, and the type is going to be type anything. Beautiful. Honestly. Oh yeah, this needs the context. Again, same thing. I like that. For lambdas, things are pretty easy. Because for lambdas, we don't yet support getting the value. You can't reflect. You can't look inside lambdas that you're given. That's basically that. So yeah, lambda would just be, for now at least, just pushing the enum variant lambda with the payload nothing. Alright, yeah, otherwise I don't even know what other types exist. Let's remove that and see that. Oh, there's var. Okay, that's... That should be unreachable, I think. Yeah, something like that. Yeah, never. Just crashes, I guess. How is those organized in here? The types are defined down here. Var primitive never. Well, that's just gonna be body.push. Tell me there's like a push crash or something. Body.crash. Is that a thing? Apparently. What? Did not expect that. Alright. I'll take that. That's weird. Yeah, I mean, recursive types, they should really be unreachable. Yeah, okay, that's what I thought. And let's actually do something similar to this. This was also for the never type. How fitting. Yeah, I don't know. Just put something in there. Sure. And this results in anything. So type anything.compile. Beautiful. Let's see if that compiles. It does. Wow. I'm actually surprised. Oh, hang on. Do I? Yeah, I panic at the beginning. Oops. Damn, that just works. What What? Okay, hang on. We just printed something without implementing any sort of print function for that. That is cool. That is cool. Just saying to anything and then formatting that. Oh, that's nice. That is nice. Damn. That's crazy. Yeah, I guess that's working. I think that's it for today, actually. Next would be looking at the... Oh, hang on. There's still some to-dos in here, I believe. Yeah, this one. Like converting an array to something, that's still something I need to figure out. Plus also the other direction. We have constructed, if you construct anything in the code, what is that here? If you construct one of these, then you should be able to use the built-in anything to value function if you know what kind of type that is supposed to be, to convert that back to a typed version. So that's what I'm gonna do next. Welcome. It's quite warm, so I made myself an iced coffee. So I have to remember to drink. Alright, first of all, making the anything, working with arrays. Let's maybe, put an example in here, like generate array, I guess. Or just like list 1, 2, 3 would also be fine. Converting that to an anything. Let's say this should fail with a to-do. Oh yeah, with something else. Sure. Alright. So array to anything. That's something that we still need to do. In here. Basically, I think we cannot use array literals because then we need to have a fixed compile time known size. But what we can do is just call the generate array function, or the built-in, and pass in a lambda that can then convert the individual items to anything values. Alright. So let's maybe do that. That should be similar to how some of the cast stuff works, I believe. Maybe. Well, at least as part of generating a new function. Oh, hang on, we already have that in here. We have this, yeah. I think now we need to have something similar called, compile array items to anything. Like, maybe not that, maybe generator, converter. The part is that this is a closure that only receives an index, and then it's supposed to return the correct anything version of the corresponding item. So I think this is just compile array items to... Let's go with that and see how that works. So this is the item type, more specifically, not the type of the array itself. And here we say that this is converting array item of something to anything. Yeah, the type is supposed to be self-contained, which Actually, I think these, I should be able to remove those because the types should already be canonicalized and so on. Maybe only turn that into assertions, stuff like that. No, not entirely sure. Alright, and then here we check is this function already defined, or are we currently compiling that? Then we just return that. Okay, fair enough. And then we build a DAG, fair enough. And we have params. First of all, we have the param for the index. That would just be the item type compiled. Yeah. And then we have another parameter for the captured array, kind of the closure. Yeah. And actually, I think the closure will not be a struct. Like the closure is usually for user-defined lambdas, but instead this is the array directly. And then what we can do is we can get the corresponding item by doing like body push, or what is it called, built-in, of the built-in yogurt built-in, probably. Let's see, is there a builder? There is. Push built-in. Oh, yeah, the yogurt. That's what I want to have a look at. Yeah, there's array get as yogurt built-in. Alright, so yogurt built-in array get. We want to call that with arguments, which will be a slice of IDs, and the type that this will return. Okay, so arguments and the type, which is going to be the item type. I've put that on multiple lines, just like so. Okay, and what kind of arguments do we want to pass in? I think the array and the index. We don't have the array yet. That would be push, what is it, get closure. I'm getting the, where the closure points to. The closure is just a pointer to the heap. We dereference that to get the array. I think this needs a type, most likely. Get closure, yeah, this does need a type. That's just gonna be this one. Oh, hang on. Just realizing this type is incorrect, because in here the type really is just a closure. So type, oh, hang on, something like that, I believe. Let's have a look at yogurt types. Yeah, closure grabs another type. Alright, yeah, and then we've extracted the item and can now, well, basically do this, push to anything. Converted is body.push to anything of the item. Let's see, an ID, a type, and a context. So the ID is going to be the item, then the type is that, the context is this. Alright, yeah, and then we just return the converted item, the anything. Cool. Cool. Yeah, there's item type for sure. Here we should actually just assume or check that the type is already canonicalized. Alright. And that means that up here, when we do want to convert an array to anything, we can now call the generate array built-in, basically. Push call built-in, you got built-in generate array. And I think this needs the length and the lambda that is responsible for generating the items. So let's see. First, the length of the array. Well, that is just you got built-in array len, I hope. Let's see, is that a built-in? Yes, array len. We call that with the array, which will be the value. All right, then what? That is gonna return an int. Yeah, and then we create a lambda. Push lambda. Let's see. That probably needs, yeah, a function and a closure and a type. Oh, the type of the lambda itself. I see. Sure. So the function will be this one down here. Yeah, compile array items to anything fun, which takes the item type and the context. So the item type is, well, primitive.args get 0, and this is the context, clean. Then the closure is gonna be body push closure of the original array, and then the type of the lambda is gonna be type lambda. I'm not entirely sure what that needs. Probably the arguments and the return value. The arguments will be I mean, this is a function that takes an int, first of all, and it takes a closure to something. Or is the closure not part of the type? Maybe not. I think not. No. Just taking an int and producing an anything. Like so. Yeah. And then we call the generate array built-in with the length and the lambda. Alright. And that's basic. Oh, that's not it, because now we have an array of anythings. Now we need to put that into this enum variant. We have this part, array of anything. Now we need to construct the enum array that contains that. But that's pretty trivial, so we just push in an array with the array of type anything. Alright. Yeah, I like that. There were no definitions named type closure. Fair enough. How does that work then? Let's see for the cast function. Yeah, first of all, the closure is not part of the type. Makes sense. How is the closure generated? Like, what is closure here? Push closure. Oh, I see. In the yogurt, we do have closure types. Oh, that makes sense. So this would be yogurt type dot closure of that inner egg type compiled to the yogurt type. Fair enough. Yeah. Yeah, here we need the type of that. That would be the type dot closure. Now let me double check that this makes sense. Yeah. Yeah, we could figure out the type here. But then again, like for every single, like even for these, we could probably figure out the type, I believe. I'm gonna add a to-do in here. Alright, so we have this push closure that needs a type, which will be a yogurt type closure of the well, the array basically. So the type. Yeah. Clean. Yeah. Useless error messages. Oh, it compiles. That's something. And it works somewhat. Oh yeah. Yeah, it does work. That is cool. Let's see. So a list really is just an array. And because a list is kind of a growable array list, you know, it has an array with not the exact same size of the list, but rounded up to a power of 2 or something like that. So this is actually an array of 4 items, and the array that and the list then stores separately the actual length. So if you push another item, it can just change this one in memory without reallocating stuff and copying stuff over. Yeah, but this is fair. Okay, I mean, arrays basically work. That's quite cool. Let's commit that. Yeah. Implement converting arrays to anything. Actually, I think a better name for that would be dynamic. Like hang on the programming languages Discord. I basically mentioned that I create this to anything function, and one of the people there said that Niva has something similar. Let me maybe pull that up. Yeah, so in Niva, which is apparently their language, that's quite cool. By the way, Smalltalk like. Hell yeah. I like that. I like Smalltalk, so yeah, anyways. They have this dynamic type, which is a really cool name, I believe. Like here they do compiler get dynamic, similar to our to anything function. You can pass in anything, and you get back this kind of dynamic object that tells you something about the structure of the value. I like the name dynamic because anything doesn't really tell us anything, Anything is like, you can store anything in there, but this can represent any type, basically, any value. What I like about dynamic is that it's just a matter of typing. It's still the same kind of value. It still has the same information as a point, or a list or something. Like this here doesn't change the amount of information to anything. Doesn't. The only difference it makes is that it makes the structure of the type available dynamically during runtime instead of relying on static typing. So I think dynamic is a much more fitting name for that. Also, like Dart, another language, also has like dynamic as a language feature, where you can, where you can have variables of the type dynamic, and they are basically not type checked. So in languages with gradual typing, this idea of I have something but I don't know the type of that statically, using dynamic for that makes sense, I believe. Yeah, so I want to rename that, which means, well, renaming this. Oh, hang on, I haven't even committed that file. Is that true? Oh, it is. Well. Like anything to the standard lib. And the next commit will be renaming that to dynamic. So first of all, name this to dynamic. Like so. Yeah, this will be to dynamic. Returning a dynamic. The built-ins will be called value to dynamic. We convert, hang on, yeah, a single dynamic thing to a value. Like, we still need to implement that, Oh, and then we can even say to static. you have some value, you convert that to a dynamically typed value. Boom, and then you can convert that back to a statically typed value of this type. Oh, that is cool. Let's maybe go with like static to dynamic. Oh, that is nice. Yeah. Does this seem fine? I think so. Then in here, this will just be called dynamic. Alright, and in the playground example, we'll also use dynamic. Alright. That's cool. What else? Oh, yeah, fixing the internal stuff here. Like this needs adjusting as well. First of all, let's rename that to dynamic and change the import in here, like so. And let's rename these functions push to dynamic. Like in general, like anything is gonna be dynamic. Yeah. Alright. And then in here with built-ins, yeah, value to anything, that's gonna be static to dynamic. Yeah, down here we just have dynamic to static, which is a much better name. Compile static to dynamic, fun. Yeah, because that's a better name. Yeah, the static to dynamic fun body. Yeah, we need like for types in the egg, these types also need to be renamed. Basically anything becomes dynamic. Nice. Yeah, let's see how these functions down here are called. Here we have compile array items to dynamic. Fun. Yeah, the function names, they are a mess, but that's fine. All right. Cool. Let's do that. Let's add, yeah, these built-ins, they need to be adjusted as well. So hang on, this is when converting the egg to yogurt, which means that in the yogurt we no longer have these built-ins, if I'm correct. Yeah, here we don't have anything or dynamic stuff that gets, those built-ins kind of get desugared in the conversion from the egg to the yogurt. But in the egg we need to adjust the names. Yeah. Dynamic typing operations. And here we have static to dynamic and dynamic to static. That is cool. Let's see if that compiles. Not quite. So down here in this list of all built-ins, this should be static to dynamic, and this dynamic to static. Like so. Pretty cool. Then this is in the lookup, where we find out the type signatures of the built-ins, and this right here would be, well, static to dynamic, resulting in type dynamic, and this is the other way around, dynamic to static, takes a dynamic, produces something static. All right. So I believe in here we need to adjust the built-ins. Oh yeah, this is static to dynamic, and this is dynamic to static. Which again, I love those names. That's pretty amazing. All right. So that's that's quite a bit. Yeah, sure. Yeah, let's maybe let's search for anything in the code base. Yeah. Yeah, these are useful mentions of anything. Alright, so rename anything to dynamic. Clean. Then the other direction, going from a dynamically typed dynamic thing, basically from an instance of this to the static version by providing a type. You basically know which type this dynamic thing represents, and then that should be, you should be able to convert that or crash if it doesn't match. So I believe we would have to, let's just call that and see what happens. I know there's a to-do somewhere in the, in the code. So to dynamic, and then maybe, I don't know, to static. We know that the type of that is list of int. So we take this list, we convert that to a dynamic thing. Then we convert that back to a statically typed value, a list of ints. Then we take the sum of that list and then we format that integer. That would be 6, I believe. Let's see. Oh, you can't call sum on list, I think. Gotta use list. Yeah, we need to import that. Like list of t, and also the toStatic. Yeah. And toStatic that takes a dynamic and type, which we also need to import. Sure. Alright. Is this the sum function, or is this the, no, function toStatic, core.toStatic doesn't exist. Well, I would try to import something that doesn't exist. I really need to fix the errors that they are not as, kind of listing all the functions that exist, but only maybe the ones that are in scope. Yeah. So dynamic, we have to dynamic on some t. Oh yeah, this would be toStatic, taking a dynamic and a type. Yeah. And that's true. Sum is not imported, and I believe sum works on an iterator of int. So we also need iterate on a list of t, so that we can do iterate and then sum that iterator and then format that. And yet that means that we need iterators. And format. Okay, yeah. Cool. So first of all, the program type checked. We've successfully created the egg. But then in the next compiler stage, when we want to desugar that dynamic to static, we don't. There's a to-do right there. Cool. Very, very cool. Let's jump into that. Which will be in here somewhere. Yeah. So basically, we need to figure out the type first of all. Like we have. First of all, let's print all the substitutions maybe. Yeah, I still need it to do in here. Alright. But basically, I just want to see at some point we need to have the type information there. Do the types get propagated correctly up to that point? Okay, so we have substitutions. T is T. I believe that is because we're basically tracking in here. We have this toStatic function, and if we would put something else in here, like a, for example, but the the toStatic function in the standard library, it accepts a T, which is a type, then this would be in this map of substitutions. Basically the substitutions from currently where that function is made available up here, all the way to where that function is defined, all those substitutions. And then here we are using that function concretely with some concrete types during like monomorphization. And here we want to replace that T with this one right here. And that seems correct. That's, list of int is just an array and a length. Cool. So we have the type information there. I think we need to do something similar to this. Something. Well, no, not similar to this. Here we could just get the type of the argument, literally. This is more similar to this one up here, where we have where we kind of need to get some argument type. All right. Let's try that. So we take these substitutions, which again, these are T maps to T. We just assume that T is in there, meaning that in the when you import the type info function toStatic function from the built-ins package, that you then use that with T. But again, like imports and exports, they are not super clean. I want to do some general cleanup and kind of refactor that code. pretty soon. Like that's the one remaining open of this big open issue in Plum. Yeah. Anyways, so we just assume that a t exists in there, and then we specialize that using our substitutions, aka using these ones. You know that we know that t is list of int. Okay, that results in an egg type. And let's not compile that right now. Let's just say that we push, oh, hang on, this one. Push call fun, compile static to dynamic fun. That can be simplified. We could just do this, push to dynamic. Yeah, this just compiles the static to dynamic fun with the type and the context, and then it calls that function with the value, resulting in the type dynamic. Yeah, so this, should I maybe call that push static to dynamic or something like that? Yeah, I think that's better. But that does mean that in here, when we have push to dynamic, yeah, this will need to change. But that is very fair, I believe. Alright. So here we just do push static to dynamic of some, you know, argument, some ID, and then the type, and then the context. Oh, look at that. It's become readable. Yeah, now we want to do something quite similar, but the other direction. So push dynamic to static. We again have, yeah, argument number 0 is the dynamic value, and then we have the type that we want to get out of there. That's everything we need, I believe. Alright, so the only thing remaining is implementing this function, which will be quite similar to this one. And let's actually copy the body compiler thing as well. So push dynamic to static, that just compiles the, well, dynamic to static fun of some type, and then it calls that function with the value, and that results in the corresponding static type. So the dynamic to static function has just like dynamic to boom. Yeah, and the type should be canonicalized, it should be self-contained, fair enough. Blah 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 blah. And then we have a parameter of the type dynamic. And then we compile the dynamic to static function body that takes things in a weird order, to be honest. Yeah. Yeah, okay. Let's just put that in there. Okay, so we have the type that we want. That should be the result of this. We have the value, which is the dynamic value. We have a context, we have a body. Alright, we extend the type 1 level so we can switch on that without going into without running into problems for recursive types. Type variables cannot be here anymore. Okay, if we want to get a primitive type out of that, then then what we do is if this is an enum, oh, I think we actually want to switch on the original type, right? We want to switch on yeah, I think we want to switch on the original value. Make sure that that is the int variant. You know, this one. Yeah. Yeah. Okay. Again, let's do arrays later. Okay, so if this is an int, then we want to not just push an enum, we want to do the opposite, we want to push a switch. A runtime switch. Yeah. Which switches on the dynamic type. Yeah, and how do switches work? I think in here we have something like that. Primitive struct enum, yeah, like this. Let's copy that just as a template of how a switch works, and then adjust that gradually. Alright, so we have a type. Yeah, and we have the type dynamic. I don't... I guess that... yeah. Okay, yeah. Basically, in the end, we just want to switch on the value, and that should result in the final type that we want. Yeah. And the individual switch cases, they do some stuff. Here we just get the name of that, and we get the kind of payload type. Sure. And then in the end we push a body. Okay, so we definitely need a case body and a from value. Oh, I see. Yeah, so basically this is the payload type, you know, and this is like the enum payload. Okay, and then, well, if the name is int, then we just, well, we know that the payload type is int. So we can just use the payload and return that. Yes. Yes. Okay. Otherwise, we have to, we basically want to crash. How's there no like push crash or something? Well, I think we'll need to do like, you know, pushing a string. I don't know, invalid. Static to dynamic failed. I don't know. And then we do case body push. Call built-in, I guess. With like yogurt built-in dot crash and a list arguments that's just the message, and this will result in the never type. That does seem quite verbose to just crash. Especially as I think that's kind of a common thing you might want to do. Well, anyways, then you have the result. And then that finishes with the result. Okay. Okay. So we should be able to compile, convert a dynamic int back to an actual int. Let's add a to-do in here. Yeah, like byte to static. And let's also add to-dos in here. Oh, this is interesting. I think that's actually valid, you know. Alright, so structs, I'm not sure about that. Struct to static. Let's just test ints and then see what we can do. Oh, lambdas are not supported basically, for now at least. Yeah. And this will probably fail. Yeah, because this is like an array and struct and whatever. But when I change that to just a number to dynamic to static int, that should work. Oh, then. Alright. Hang on. Oh yeah, no, this is the other way around. Alright. Compiles at least. And it crashes. Yeah, struct to static. Perfect. Well, not perfect, but that was what was to be expected. So now we should be able to convert that 42 to a dynamic value and that back to an int, and then format that integer using the usual integer formatting. And that works. Okay, that's pretty cool. Yeah, next up I guess bytes. Which will be pretty similar to integers. Let's see, we extend that, and then if this is the byte variant, everything's fine, otherwise this failed. Yeah, that's basically it. It has to be the byte variant. All right. Structs. They are kind of. Oh, they are weird. So structs are weird because they contain an array of name-value pairs. And you might wonder why use an array in that point, and not something that kind of better represents the intention, like a map from string to dynamic. And the thing is that this dynamic, static to dynamic stuff, is really like the core of, like it is an interface with the compiler itself. And maps are complicated beasts. Maps have equality, function, lambdas, and hashing and whatnot. And I want to keep that interface between those two as small as possible. And also, in practice, your structs won't have so many fields that it's worth putting that in a map. Like, let's be real, if you have a struct with even like 10 fields or something, just iterating over an array is probably faster than putting that in a map. Yeah, so I think what we need to do is, when converting a dynamic value back to a struct, we need some way to, basically a get function for that. So imagine, you have a get function, I don't know, given some fields, which is an array of fields, so these kind of things, and then a name, which is a string. This should be able to give you the corresponding dynamic value. And the way that works is it should just iterate over the fields. So it should do fields.iterate.find, I don't know if find is even a thing, but basically, if given a field that has a name and a value, you want to find one that a field name equals the name. Now let's break that up in multiple lines. And then that returns you what, maybe? So you can unwrap that. And then, given that field, you then return the value, something like that. Of course, the compiler needs to implement something like this in order to implement the dynamic to static conversion. I won't use iterators and all those fancy abstractions. I'll just have like a function that is recursive and passes an index to itself and use that to kind of iterate over the array. Yeah, but still, this is fine, I think. Like, this is way more complicated than the other direction. Static to dynamic, we kind of knew the structure of the type, and we only had to create enum variants. The other direction, like here, we could be given any dynamic value. So when trying to convert that to a static one, we really have to match that and kind of inspect that and do a lot more work to extract the correct information out of that. Yeah. All right. You know what? Let me take a break and then continue working on this. All right. So converting a struct to static. Basically, we need to check that, first of all, the dynamic is a struct. So let's do that first. Yeah, something like this. Yeah, if the name name is struct, then we just get the payload, otherwise we crash. And instead of just getting the payload here, the payload now is this one. It's an array of fields. So we need to convert those into a struct. Yeah. So let's. How do we construct a struct? Probably with like casebody.push struct of some fields, and the fields have to be a map from string to ID. And the way we populate them is by iterating over the field types. So for field type and field types, we basically get the name, yeah, something like that, and we get the field type, which is the value. Oh, it's like that, right? Yeah. And then we basically want to, first of all, find field dynamic in the array. And then the second part is parsing that. So dynamic to static of that field. And then we push that to our fields. So that then down here we can just push a struct of those fields with the requested type. All right. So the big question is finding the field in the array. I think I'll add a function for that. Yeah. Something similar to what we did up here. Up here we had this function and then the body, and at some point it called some helper function, this one, compile array items to dynamic fun. And I think I'll do something similar, also like a helper function down here for finding a field with a given name. Yeah. All right, so this function takes an array hang on. Find field in array of dynamic, maybe. And we are given a name. But we don't even need a type. We only need the name. Yeah. So we don't need that. Actually, this is just a single function. We only ever need one compilation of this function. All right. So we created DAG. The builder, all right. and then we accept, first of all, an array of dynamic. Hang on, type dynamic fields. Yeah, that one. Yeah, an array of structs with a name and a value, which is a dynamic. Yeah. Yeah, we accept that array. We accept an index. Well, let's say first of all a name that we want to search. So that, and then an index, which will be an int. All right. And then what we do is we what's going on here? Well, we get the item at the index. First of all, oh, hang on, no, we need to check whether the index is larger than the size of the array. Yeah, this one. Nah. Yeah, okay. So we do body.push some switch, and the switch needs is at end, maybe. Yeah, maybe call the built-in function compare ints. Call that with the index. Okay, get the array length maybe. Which is array len of the array, and that results in an int. Then we check, well, we compare the integer to the index to the length. That should result in type ordering. Then we should be able to switch on that. Takes a condition, takes cases, takes a type. All right. So yeah, I think I'm just going to inline the condition in here. Then it takes cases, which is map from string to body. So in our case, that would be less or equal or greater. And yeah, we do different things here. If the index is less than the length, then compare strings. Or first of all, get item, get field from array, compare strings. If they are the same, return value. All right. Yeah, and in this case where they are equal, I mean this is unreachable, so, but I guess in both cases we'll just create the sort of body for the switch. How does that look in here? Like this, we create a new body builder that takes parameters. All right. Yeah, so we need something like that. The equal thing does not take a parameter, I guess. Doesn't need to. Or at least like type nothing, I guess. Not sure if that's needed. No. Let's leave that there, and then we just crash, I guess. We crash by creating a message. Field, not a map. Yeah, and then we crash. So case body dot crash. Oh, that's not a thing. I see. But for built-in, we got built-in dot crash with the message resulting in a type never. I should really add some helper functions on the builder to make that more, to make that shorter. Then you say never, and then you just finish with that and return that. Alright. Yeah, and the same thing, I mean this is basically unreachable, so we don't even need to have a nice message here. Like that. Alright. That's cool. Now this case, though, we need to get the field from the array, so basically call yogurt built-in dot array get is what that would be, of the array and the index that returns us an item. So we have to, where's that? Oh, the type of that, we don't need to pass that down here because we know that type of that is type dynamic field. Yeah. Boom. Then we need to get the field name. Body.push member of that field, the member name, which has the type string. Nice. And then we want to compare those. Well, I guess we need yet another function down here. Compare strings. this doesn't need any extra info, it just builds a body, it takes 2 arguments. That's it. Yeah, those are both arrays. Yeah, and then we just we could check that they have the same length first of all. So array len I guess, yeah, first get the bytes. That would be body.push member a utif 8 bytes, and b bytes are b utif 8 bytes. Then the length is array len of a bytes, that gives us an int. Whereas the b len is the length of the b len array. Yeah, now we want to compare those two, so we just switch colon compare ints with a len and b len. If they are less, then we just return false. Well, yeah, that's not correct. Now we need to create a case body for that. Yeah, case body takes nothing, and then it doesn't do this. Instead, it just pushes an enum false with the payload nothing, and the type bool, which doesn't yet exist. Interesting. And then we return that. I mean, yeah, let's inline that down here. Like so. Cool. Yeah. If one of them is greater than the other, same thing. If they are equal though, then we want to iterate those bytes. So I'll just have another function called compare strings reg, I guess. And this one takes an array of bytes and another array of bytes and an index. And then we don't need to do this, we don't need to do this. I mean, yeah, this is maybe useful. Yeah, sure. Yeah, and then if the index is less than the length, then we want to get the bytes. So that would be calling the built-in array get of a, which is some bytes, the item at the index. That's going to be a byte. All right. Does that fit on a single line? Not quite. Fair. We do the same for B. And then we have to compare the bytes, which doesn't work directly, I think. We have to convert them to integers to be able to compare them. Oh man. So what we do is we call compare ints of a byte, well, of, first of all, body push call built in int to byte. Is that not a thing? Hang on. Oh, lower byte and byte to int. Byte to int is the thing there. Byte to int, that's what we want. And byte to int of the a byte. That returns us an int, which still doesn't fit. Like, well, yeah, only a single argument, and I know. Then the second one, I see, is the b byte converted to an int. We compare those ints, giving us an ordering, and then we want to switch on that. Oh, hang on, all of this has to work on the case body. Yeah, and not switch on it like this, but instead on the case body push a switch on the ordering using a map. Alright, this should result in a bool. Like that, okay. Phew. So, if this is less, then we actually just want to return false, similar to what we did up here. If they are greater, we also immediately want to return false. If they are equal though, we want to, well, call ourselves recursively. So case body dot call fun. Which function? Well, the compare string is rep fun. With what arguments? Well, the same arguments that we were given, so a, b, and index, although the index should be one more than before. So a, b, and case body dot push add is not a thing. Interesting. Call built in then, I guess, which will result in a bool. And that result will then be used to finish this. Alright. Yeah, this has an A, it has a B, it has a case body. The index plus 1, so yogurt built in dot add ints, of some arguments resulting in an int. And the arguments in here are first of all the index and then case body dot push int one. All right. Pretty cool. Pretty cool. Ooh, all right. Damn, this is quite long. I think the next thing after this is not is fixing the builder to be more ergonomic. Yeah. So we did this. What's going on there? This entire thing was the switch. You see? So this is the result of the function. Okay, yeah. Man, that is crazy. All right. Yeah, let's make that. There will probably be errors, yeah. Oh, it's not even finished. I see. So here we got the field name out of there. Yeah, then we want to compare the strings. So we want to do call the fun, well, compare strings fun. We want to call that function with some arguments, namely the field name and the name, our name that we want, and that's going to result in a type bool. We've compared the strings. Okay, and then we want to, oh yeah, this needs to have a case body first of all. Yeah, where we these need to use the case body, and then we do push switch. We are switching on whether that matches, and well, if they do match, then we what do? We want to return the value. So I think we'll need to do this. Body builder body.dag, okay, and then we get the member similar to the field name. We then get the field value. All right. Now we're getting somewhere, you know? And then we finish that in a case with that value. And this one as well, with the result of the switch. Okay. Otherwise, if they're not the same, we want to call ourselves recursively. So we want to have a new case, and what we do is we create a field value. Hang on, case body push member. No, not quite. We want to call ourselves with an extra index. So we need the array, the name, and then the index. Alright, so let's do that. Let's do case body. Let's just immediately finish with case body.push call fun, well, ourselves, with the array, the name that we want to find, and then the index plus 1, which is something that we've done in the string comparison. Somewhere here. Let's see. Here. And that results in something in a dynamic. All right. Damn. That is quite verbose. This call doesn't work, okay. Why not? Because it takes a yogurt bodybuilder? Oh. Yeah, no, that doesn't make any sense. Field is not in scope. Well, that's unfortunate. Yeah, indeed. Oh, hang on. Oh, this one is supposed to be the field. Getting the indexed field from the array. Type bool is not a thing. That is surprising. Oh. That is honestly surprising. Mm-hmm. 268. No idea what. Oh, dynamic. Yeah, that makes sense. Oh. Oh, yeah. And now we want to find the field. So we do case body dot push call fun. Our compile find field fun and stuff. That needs only the context, I believe. Yeah, and then that one. Maybe not. Oh, I see. Yeah, of the surrounding. Yeah, we call that function with some arguments, namely the fields. So that would be the payload, which is the array. Then this needs the name and the index. And yeah, because it takes the name as an argument, we don't need to, like, this is not a thing. Ah, that doesn't fit. No. Okay, array, name and index. Array, the name, which should probably be a key, yeah. Like that, and then the index, which is case body and 0, and that results in the type dynamic. Yeah, and then we pass that field into the correct type. Beautiful. Using the field type, I think we need that as well. Push member. This is the signature. We need a type. True. This results in a type array of bytes. This switch does not have a type, and the compare string is fun. Yeah, the type is supposed to be and what exactly is that checking? It compares the lengths. Alright. Hang on. Compare strings. It compares the lengths. If they are less or greater, then it returns false. If they are the same, then it shouldn't crash. It should just return true. And then that entire thing returns. Oh, I think there will be a lot of these kind of weird semantic mistakes in the code. Array is not in scope, of course it's not. We compare two strings, so we check if the length is the same. What? Oh, I think, in here we actually don't just want to result in true. Instead, we want to, this should already be the result of the string comparison. So we really just want to call, in here, if the lengths are equal, then we want to call the function, this one down here. Compile this one. And we want to call that with both the byte arrays. So A bytes and B bytes. And that's supposed to result in a bool as well, that we then use to finish this switch case. Alright, so this one is in compare strings recursively. Yeah, we need a result of this. That is a bool. Hang on. Nope. That's still weird. Compare strings recursively. We compare the index, the current index, to the length. Yeah, we already know that both strings have the same length. Alright, so if the index is less, then we get the bytes, we can compare those, and depending on the result, we do an early abort with false, except if they are equal, then we call ourselves recursively, which we can just do using that. With the index plus 1. Yeah, that makes sense. What was this? There are too many nested switches here. Oh, this is if the index is less than, right? Yeah, if the index is less than the length. If the index is equal to the length, we've reached the end of the switch. Then we just the end of both bytes. So we can just return true in that case. Yeah, they are equal because we've compared all the individual bytes. And greater can basically not be reached, so this would be, yeah, crashing. Alright. I like that. Cool. We still need a type here. That makes sense. So this results in a bool. Alright, then up here we have compared strings apparently. Nice. And then here we have a push switch. Yeah, which results in the type dynamic. Yeah, the field value is of the type. Oh, not type string. Type dynamic. Same here. It's really easy to forget the type of the switch. This is in which function? Compare find field in array of dynamic fun. Well, store this. What? Find field? Was it find field in array of dynamic? Yeah. Not sure about that. Not sure about that one. This one right here results in a dynamic value. This in never, this is in never. Okay, so the entire thing should be dynamic. And this should also just be in there. And the result of this switch is supposed to be known as the result. Alright. Slowly we're getting somewhere. Push dynamic to string, to static, what's going on there? This needs the context. All right. This doesn't work, probably because this is the wrong kind of type. Oh, it compiles at least. Okay. Something's going on there. But that is actually like a fine, an actual plum error. So what's going on here? We have a field. Oh yeah, right. Need to do that. Boom, there is no function named equal in scope. For strings, yeah, that would be useful though. So let's import that. All right. What's going on there? Oh, there is no equality for strings. That is surprising. Indeed, there is not. Well, yeah, of course you can compare two strings. That would just compare the underlying bytes. So that would be a dot UTF-8 bytes compared to b dot UTF-8 bytes. And that probably means we need to have comparison for the I see, arrays of bytes. That probably doesn't exist. So let's add that. So comparing an array and another array, you can do that if you pass in a comparer, which is a lambda that takes two t's and returns a bool. If you do that, then you can compare two arrays. The way that works is I guess it first checks if the array length is the same, so a dot length is that b dot length. If it's not, then it just results in false. If it is, then we actually, I guess we do a dot iterate. Like we zip a dot iterate and b dot iterate, and then we do some more stuff. We check that all of the items here, both, which will be some struct, I believe, I'm not entirely sure. How does zip work? Yeah, an iterator with A and B. Alright. Yeah, it should have an A of type T and a B of type T. And yeah, then we can run the comparer with those A and B. Yeah, and if that is true for all the items, then this entire thing, the entire array is equal to the other. And of course, we also have an equals for specific arrays, like an array of bytes. By calling compare with A and B, and then a comparer that takes one byte and another byte, and it runs A dot to. Oh, hang on, there is a comparison for bytes, isn't there? Should be, at least. No, there is not. Well, comparing bytes. I think we'll just do the a dot to int and compare that to b dot to int. Yeah. And then in here we can import that. We can do we can import like equal for bytes. We also need to import a zip. And all. Oh yeah, we also need to import the byte type. And the comparer, try to call them with wrong types. Well, would be helpful to know the types there. Oh, and oh, I see. Both is the one. So here we want, hang on, both dot a and both dot b. Like so. Alright, we have this one. An iterator of a and b of t, and then a function that takes there's array.all, which only takes these. No, there was all that takes an iterator and a predicate. Oh, hang on, array.all. Oh, that is this function that we are currently defining here. Oh, I see. I see. We need to import that. All with that and a predicate. Very important. Okay. So then bool. Hang on, bool does exist. In call byte. Oh, and also comparison for integers. Yeah. Slowly we're getting there. Okay. Okay. Find. Get fields. Yeah, right. We have find. Interesting, that returns a maybe a. Okay. Find with an iterator a and a predicate from a to bool. Pretty cool. Iterator. Yeah, please find with an iterator of a and a predicate that takes a to bool, and that returns a maybe that we want to unwrap here, so we also need the maybe type first of all, and then the unwrap function. Alright. In dynamic. Oh yeah, this refers to bool, means we need to import bool. Just linking up those types. Oh, that worked. Hang on. I mean, yeah, that makes sense, I guess. This works. Huh. Can I do this sort of thing? You know, we have some point, and then, oh no, that's not good. Static to dynamic. Oh, okay, a crash. That's actually fine. Static to dynamic failed. Oh, hang on. Static to dynamic. That can't fail. Why can that fail? Oh yeah, this is the other way around. This one too. This one too. All right. Expect a byte. Yeah. Expected int. Okay. Well, that gives us a hint. Let me take a short break. Okay, so I guess where's the int coming from? Do we correctly, you know, parse the field? How do we do that? We have this struct. We go over all the possible dynamic values that can exist. If this is something else than a struct, then we would see expected struct. That's not what we get. We get expected int. So at least we find out that this is a struct. That's cool. And now we want to build the fields. So we iterate over the field types, which should be a map that maps x to int and y to int. So for x, we would get the name and the field type int. Then we would call compile find field an array of dynamic fun. Basically finding a field with the name x in that array. That returns us a dynamic thing. And then we convert that to an int. That field which is defined there. Yeah, that is connected the right way, at least. It's kind of weird that field is shadowed here and here again. But, I mean, what are you gonna do, right? Alright, so we have this. Then, like, this looks fine. Push then, this one though. Does it return the correct dynamic value? That's the question. Compile find field in array of dynamic fun. Let's see. Oh. If we get this, then things are fine, probably. Find field in array of dynamic fun. Alright. What we do is we get the array, which is of the type dynamic fields, correct. We get the name and the index, and those are also the arguments that were passed in above. Alright, so what we do is we check is the index less than the length. Alright, if it is, we do stuff, otherwise we crash, and here we crash as well. Cool. So in the case that works out, for example, let's say that the index is 0 and the, at index 0 in the array there is the correct field. Then what we do is we call the array get, giving us the field. That's a dynamic field. Then we get the member name, which will be a string. Then we call compare strings. Yeah, that's correct. Which returns a bool. We pass in the name that we want to find and the field name. If that matches, then we get case push the member, we get the value out of that field. Correct. And then we do case body.finish with that field value, and then the surrounding code does case body.finish. And then the surrounding code has this result, and then it puts that in the map. Okay, that seems correct. That does seem correct. I don't know about that. Expected int. Why? Why an int? Like, what does it? What is it instead? It's maybe if the name is an int, then we return the payload. Otherwise, I see we'll just push that string. We could have a better error message there. Something like push, build Oh, hang on, the name is compiled unknown here, because we are currently compiling only a single case. So we should be able to do this. Got struct. Okay. Uh-huh. Just to rule out any errors, let's run the yogurt directly. So we know that the part in the compilation pipeline is, that the error is in the first part of the compilation pipeline in this conversion to yogurt. Plus we also see in the intermediate expressions. Like this is so nice for debugging, honestly. Okay, so the main function is called with 5. We call toDynamic with this struct. Makes sense. And then boom, what we get back is this. Nice. So this is an enum that tells us this is a struct. And then it contains an array of struct fields. The first field has a name, which is the x probably, value 42. Second field is, well, one more. I don't know ASCII or like off the top of my head, but seems reasonable. And then this also contains an int. All right, now we're calling toStatic. On that struct. And we call that with our original struct. Hang on, toStatic. Oh, hang on. We call that with this, kind of dynamic value, but then the type int. Do we really do that? We do. Okay, so this is not an error in the compiler, this is actually just me being stupid. So let's say we have a type point. We should be able to say toStatic point, and now that should match. There is no matching function named format for that. That is indeed true. So let's maybe access x and just format that, I guess. Ooh, nice. Struct toStatic. And that was the to-do that I can remove in here, I think. Yes. That switch does exactly that. It converts the struct to a static value. So let's see. Some errors, okay. So let's see. toStatic. With this value, and then the type of a point. Very nice. So that calls dynamic to this one with this value, which is pretty amazing. Yeah, and then that calls find field. Oh hell yeah. And it calls that with, first of all, an array of the struct fields, and then the field x, as we can see here, and then the index 0. To do that, we compare the strings, and these should be equal, so we do compare strings rec, and then it says zip, it should have unequal length. Compare strings rec. Okay, and do we do zip over here? We don't. Compare strings rec. What do we do here? We have the oh, I see. Do we like provide the wrong number of arguments to this function? It needs an array of bytes, another array of bytes, and then an index. The first, oh, I see. Like this one. I see. I think it misses the arguments there. Let's see. Here we call this rec. Oh yeah, with the index case body dot push int 0, please. All right, yeah. That's cool. That's super cool. So we are running this function, and then we want to convert that back to a static one. So we try to find the field in this, in this array. We try to find the field x. It turns out that exists, and it's this dynamic. So then this entire thing, this dynamic to, oh hang on, what is this? Oh yeah, then we call dynamic to int using that. We get back the int. Then we do a find field of the other field, this one. Yeah, we compare the strings of the first one. That doesn't match though, returns false. So we call that with the second one, that returns true. So this returns the dynamic int4, and then we convert that to an int, boom. And then here we have successfully converted that dynamic value back to a static one. Amazing. Amazing. Yeah, and then we format the 42. I mean, sure. So, what's going on here? Left is not an int. On some subtraction. Subtraction happens when comparing two integers. So let's make sure that these are all ints. The index is the result. Hang on. No, the index is not an array of ints. The index is just an int. Yeah. Just to be sure, let's go through all of these. In here we compare the index, which is an int, to the length, which is also an int, which is the result of calling arraylen. Makes sense. Yeah, this one alan and blan, the results of arraylen, is an int. This one I just fixed, I believe. Yeah. And this one calls byte to int, which results in int. Okay. Yeah, 24 bytes makes sense. That's the size of an array. It works. Output's 42. I mean, that is cool. That is honestly cool. Nah. Okay, I'm gonna commit that just because it's a lot of it's gonna be a lot of code, and I want to have some like checkpoints in between. All right. First of all, I think I want to commit some of these very basic, adding comparison for arrays of bytes, for example. Yeah, that's just a fix. Yeah, sure. Very generic and improved standard type. And then this one's the interesting one. Type bool. Dynamic to static. Yeah. Start implementing dynamic to static. Would be an okay name for that, I think. Yeah. And actually, I think the struct was by far the most complicated one of the bunch. Like we can, let's maybe look at that. We can already kind of deserialize bytes back to a static form, as well as ints. With types, you just can't do that by design. That's fair. With arrays, yeah, okay, that makes sense. That's going to be some work. Struct, I think, were by far the most difficult one because we had to compare strings and stuff like that. Lambdas, we don't need to do anything. You can't do that. Enums, yeah. Okay. Before I do anything further there, I think I want to make the builder prettier. Like this code here has very low density in information. Just push call built-in, and then the built-in, and then the arguments, and then type int. I mean, for some of the built-ins, I just want to have something like push byte to int that accepts a single argument, a byte. And it's obvious that this returns an int. And wrapping that in a list and slice, having this prefix, like we don't need that. And maybe even like push can be renamed to something a bit shorter. Okay, but first something that was bothering me about the names here. In a lot of cases we use case body. Is there any reason for that? Because this really is like you just need to accidentally write body in here one time and you append to the wrong body. That is error prone. So, and I think in all the cases where we do that, we actually can just shadow the original body and things will be fine. Yeah, the original body is somewhere there. So yeah, let's just do that. Replace case body by just body, if that works. Same here. Yeah. Same here. And then here nested case body and case body just shows that shadowing makes sense. So because bodies are by definition like lexically scoped usually, so if you need anything from the outer body, you don't need the body itself, you only need the expressions from there that you want to capture. Alright, so we've done that. Oops. Just wanted to go here. And that should just still work. If it does, then I'm happy. Yeah, alright. Then next, the builder. The builder is horrible. Yeah. Like this is one thing I could do. Also the push prefix I think doesn't really make sense. You know. Just do this like put int in there. Or string. Or array. Or struct. Similar to I think the egg builder does this exact thing. I mean, I can just do this, I guess. So much push. All over the place. Yeah, for the enums I kind of need to fix the syntax. Alright, so first of all that. Then your int doesn't need a type because it can figure out the type. That makes sense. Same with a string or array. I think what makes figuring out types difficult is that those types should be canonicalized. And for example, we can't just, even for arrays, we can't just accept the item type in here, because we can't just wrap that type with an array. If that type itself, if the item type is, I don't know, some sort of recursive array, if we just wrap that in an array, that's no longer canonicalized. So things are, it is weird that you have to put the type all over the place, but I guess it's okay. That's something I have to live with, at least. Yeah. This one, though, nope. Like that. Weird to do. Oh yeah, a couple of these can probably fit on a single line now. Maybe. I like having dense code, so. Let's see. Yeah. No. Nice. Like, this is super cool. You know, body.nothing, that is concise. Way better than before. I mean, that doesn't really, no. Hang on, no, that was actually wrong. Yeah, no, this is type field is actually type dynamic field. Oh, hang on, no. Oh, I see. It's type info. Oh, I don't know about that. Oh, I don't know about that. Yeah, but I think I actually want to have separate ones for those. Type info. And then these have fields. That field is this one. You know, it has a name. It has a type, which is that. But then these here, they can just immediately be that. Yeah. All right. And then also fields, plural. Kind of the array around that. And that means that in here we can just do that. Oh yeah, and variant is probably also useful. Yeah, and in here we have type. Type info variant, that is just type info field, and variants is fields. Something like that. So that in here we can just do type info field dot compile. Pretty amazing. And for this array we can do type info fields plural dot compile. I'm also thinking about putting the types up front, because the calculating the payload is usually a lot bigger. It takes up more space, especially in here, for example, with the switches. Down here, like type dynamic, you don't remember what that was. Oh yeah, we are in a switch up here. So let's change that. Let's say that we take the in here we have an array, and before taking the items we just put the type up front. Same for struct. Same for the member. See, that's kind of weird, but I guess it makes sense. enums for the switch. Oh well, maybe not at the front, but maybe in here. I know it's inconsistent, but let's do that only sometimes. Yeah, like in here, let's have the condition, then the type of all the cases, and then the actual cases. Then again, this is weird. This is weird. Let's not do that. Let's put the fields at the end, as it should be. Yeah. Alright. So, here we have an enum type variant. No, we don't need that. We just build up IDs, and they have the type variant, which is type info variant, and this one down here is type info variants with an s dot compile. Nice. Very nice. Then this is also not canonicalized. You know, the type, what is it? This one. Type for the arguments. Well, first the lambda itself, I guess. That should just be this one. Oh, let's maybe compile. Yeah, this is the type info. And this is the lambda. Except these recursive ones, they actually point to type infos. Like so. Alright. And within this lambda, we can just have a recursive type here, I think. Oh, hang on, at least for the arguments. What was it before? Yeah. Type recursive 3. No, type recursive 3 like this. No, hang on. In here, I think. Type recursive 3, which would be 1, 2, 3. Yeah. a lambda contains this entire thing again. That makes sense. An enum doesn't though. An enum just contains, oh, yeah, I should have copied the original type info. This enum. Arguments is an array of these. The return type is just one of these. Like so. Yeah, and in here the lambda is just recursive 3, which is 1, 2, 3 points up to that one. All right. I think that's actually the most, efficient representation of that. Oh no, hang on. In here, the lambda can be simplified. Into that, I believe. 1, 2, yeah. And then we have lambda args as another thing. The args is basically just that. And an array of type infos. Except in here, in that array, this is, oh yeah, this is an array of type info, that makes sense. At some point, do we have an array of types? We do in here. This can just bubble up to that. Arguments is recursive 3, which is 1, 2, 3, points up to this array. Yeah, alright. Well, that was surprisingly complicated. Let's see. The lambda arguments is an array of not this, but type info lambda args. Makes sense. And then this entire thing is type info lambda. That's it. Clean. I like that. The cool thing would be if the types come first. Like so. We could even put that on the same line. Same with the enum. That is kind of bothering me. Yeah, let's do that. At least just for the struct and the enum. Where that is actually kind of useful, I guess. It kind of makes sense. And also for the switch, where we have just so many cases, usually. and they should come last. All right. Yeah, the type and the values. Clean. Oh, I'm just realizing I'm doing this every single time. I can factor that out. I can say, you know, variant and payload. Is something. And then down here I do body.enum, variant and payload.a, variant and payload.b, and of course the type is type info.compile. So then in here I would only have to do, you know, like a tuple of that. In here that comes first. Like so. Yeah, same here. Move that over there, this over there. Boom. And of course this entire thing is just a tuple. Clean. Yeah, this is that. And this enum, we don't need that, we can just do that. A tuple. In here, same thing. Clean. All right. Yeah, much simpler. Much simpler. It does make sense to also do that for the array, I believe. Yeah, move the type to the front. Oops. Yeah, and that's the type of the entire array. So in here that would just mean switching these around. Although I could also say I'm creating kind of body for the slices for the this. Look at that. Oh, that is clean. I like that. Oh, that's amazing. Yeah, let's do the same thing here. Kind of align this more with the natural scoping. All right. Then. Oh yeah, I think the whole type info stuff that should go into its own file, I believe, because that's not like a core part of the builder. Cool. Yeah. Then in here there were some errors apparently. This is just parent. Sure. Yeah, this is just int. This is just string. This is just something cool. Where we flip these around and we calculate the fields in there. Like so, and in general. For the switch, we get the condition, then the type, then the cases. Clean. That is so clean. Okay, then lambdas. Yeah, closure should also be flipped around, I believe. Your member is really like an operation, but enum is, it creates a new value. Switch, I don't know, but closure definitely creates a new value. Boom. Get, again, I'm not sure, because this is, you know, a bit more iffy, or call lambda or something, but all these that create a new value, I think those should be, take the value up front. what is kind of bothering me here is that there were a lot of variables and there was no real structure among them. Like the fields, for example, they are only used, let's double check, yeah, they are only used down here. And the field types, they are, yeah, they are only used in here. So really, all of that just exists to create the struct. Let's put that in scope, you know. Well, the struct type again is used in there. Well, I don't know. Oh, but you can always do, you know, body.typeOf, so I think that's fine. Yeah, let's move that in here, and then struct type is something, and then this just results in that. And instead of this, let's put that directly in there. Oh, look at that. Something that gives me structure. Even apart from the fact that this is called struct. Struct containing captured. Something like that. Yeah, here struct type doesn't exist because that's just body.type of struct containing captured. And that's fine. Closure type, is that even, that's used down there. Let's not use that, let's only put that in here. Like that. We build a closure of the type closure of type of struct containing captured, and it contains the struct containing captured. Makes sense. Yeah, so the only variables we have is struct containing the captured variables and then the closure. What? And then here this would be, yeah, body.type of closure. Mm-hmm. Nice. That there was body.typeOf. Oh, but that's not something runtime like, that's just compile time stuff. Okay, fair. Static to dynamic should be dynamic to static, yeah. I'm gonna create those. for this, I'm just gonna add a crash function in the builder. Just like we have call built in. Instead I'm just gonna have call, just crash. With a message, which is gonna be an ID, and that just does body dot call built in yogurt built in dot crash with the message that results in yogurt type dot never. Nice. And then maybe also even an unreachable. That just does crash with an empty message. Yeah, something like that. And then in here, this never thing should just be unreachable. So this is just unreachable. Oh, but the to type. Well, you see, this is okay. I guess. Fair enough. Array len. Yeah, let's make that a thing. Nice. So that's just array len of from. So much shorter. So much shorter. Yes, the closure type needed. It is. Yeah, no. I mean, the closure doesn't need to do any sort of canonicalization or something. So I think for the closure we can actually figure out the type. Oh. Oh yeah, no, that makes sense. Yeah. Damn. Yeah. Array get. generate array here.
All right. I think overall that got a bit simpler, which is nice.
Now let's look at this monstrosity and see what we can improve. Way simpler. Hang on, that doesn't make sense. Yeah, like that. Oh, this is unreachable. Oh. Again with a custom type. You know what, let's maybe make it so that unreachable and crash that they can take a type. for. Pile dynamic to static fun body. Alright. Mm-hmm. Mm-hmm. Lastly, there's a lot of ceremony when creating a function. You know, we think of a signature, then we do a context is defined of that signature, or are we currently compiling that? If so, then we just return that, otherwise we start compiling that signature. And then in the end we define a function and we're done compiling. And that's just a lot of stuff that's going on there. Yeah, first of all, we don't need running. We're just compiling functions. Yeah. Yeah, this could return maybe, you know, a result. Some sort of maybe. Let's say result. Then we could basically check, are we currently compiling that? And also, like, if that is already defined. Then we do if is defined or is currently compiling. Then we don't need these anymore. And we don't need define, because we can just say that. Oh, this can also keep track of the context. define that and we're like done compiling. Yeah. Mm-hmm. Nice. And then you can just do let's see. You can just do you have the signature in here. And you can just do context.start compiling using that signature. You don't need to do this. Instead you can do or if that didn't work, then you can just immediately return. The result error basically means it doesn't mean something went wrong, it just means you don't need to compile that. It's already done, it's already taken care of. Yeah. And then down here you can just say compilation done with his signature. Now with the function and that, maybe that also returns the signature. That would be nice. Mm-hmm. Then you can just inline the signature in here. That's also quite nice. Nice. Yeah, so with the cast maybe. Yeah, this becomes a bit simpler. Because instead of this, we can just do, first of all, that. And then this becomes context.start compiling this. Or immediately return that. Okay, maybe having something like define is useful. And that basically starts the compilation, aka it doesn't check that. Would push something to the stack, but that doesn't really make sense because then immediately we pop that again. So the only thing we do is that. Oh. Then we can even do quite late. I guess the next step would be, well, converting other dynamic things to static ones, such as enums, arrays. That's basically it. Yeah, these work, these kind of work. I'm not sure about that. These work, yeah. So arrays and enums. Nice. Alright, let's see. So the arrays or enums, I guess let's do enums first. Which means we'll probably have to go to the dynamic yeah, converting enums to static thing. So we have the enum as a dynamic, dynamic part. Let's just copy that from structs, I guess, and then adjust that as needed. Alright, so we are building a switch. That makes sense, because we want to switch on the dynamic and make sure that it's this one, dynamic enum. So we have cases, and if the name is enum, then we want to do something, otherwise we crash, because we expected an enum, but the dynamic is something else. And then in here we can check that, well, if this is an enum, we actually want to create an enum. And that needs the type, alright, and that also needs the variant and the payload. So in this case, the payload of this enum entry is exactly this. Which means we can get the name and the payload from that. Let's do that. Let's kind of move that in here, I guess. Yeah. And then let's do, well, the value is basically body.member of the payload, the string value, and that is gonna have the type dynamic. So type dynamic. Perfect. And then we also need the variant, the name, the variant, whatever. That's going to be the first part. This one. Oh, hang on. But when creating that enum in here, we actually need to know the variant at compile time, because that expects a string. So I think what we want to end up with is basically a switch. Oh no, hang on. Not even that. I think we want to... Let's write some pseudocode. Converting a dynamic to... Let's say we have an enum foo, which is an int or bar. Then when you want the corresponding dynamic is going to be enum, and then it's, for example, going to be this name foo value 5. Oh, sorry, value is another dynamic, so this is like int 5, something like that. When we want to convert that back to this type, we first of all switch on that dynamic. If it's an enum, and we do something, otherwise we basically crash. And if this is an enum, then we want to... Oh, I think we want to... The enum has a name. We want to compare that to foo. I see. Like this. And if the name is foo, then we'll just create the enum variant, you know, foo, and enum.value to static int. Otherwise, we're going to try the next variant of this enum, which is bar. So enum.name is bar, and then we switch on that. If the enum is bar, then we'll just create the bar variant. Otherwise, you know, crash, basically. So we want nested comparisons for every enum variant. All right. So we've checked that this is an enum. So we're basically, you know, inside this case here. And this is the payload. Yeah. Then the variant name is the payload's name, and that is a string, like so. All right, so we have the name, the variant name, and we have the value. And now what we want to do is we want to have nested comparisons here. Phew. All right, so let's go through all variants, I guess. Let's do like body dot, what is it, like we want to do a string comparison of the we basically want to do that for every not of every entry in the dynamic type, but of these variant types up here. Something like that. So we want to do a switch, and then we want to compare the variant type.key, which is a string, we want to compare our variant name string to that. Yeah, and then this is gonna have some type, and then we have cases. Basically, if the name matches, we want to do something. If it doesn't match, we want to do something else. All right, so if the name matches, okay, the type of this entire thing is the type that we want to get out of this. If the name matches, then we want to create the corresponding enum. So that would be this one, and way simpler. So body.enum of type.compile, and then that needs a name, which is gonna be the variant, this one, and then the payload, which is going to be this one, this value converted to a static. I think like dynamic to static. What does it need? It needs several things, like the payload, the context, something else. Yeah, otherwise we want to nest these. Oh, you know what? Let's have like some expression that we then wrap multiple times. Yeah, body. Well, inner body, something like that, is well, I want to create an enum case body. How is that? I think we need to create some sort of body builder and then give that a param and stuff like that. So let's do that. Let's say we create a body and a payload. Yeah, this is like, not sure. Let's just do type nothing, I guess. Yeah, and that's body.param. Alright, and then what we want to do is body.crash. No enum case matches. And yeah, that's a bit confusing, you're having this inner body, but I think it's gonna make more sense when I do this. So in here, this is just a body that crashes. And then for every enum variant, we kind of wrap that inner body. So for the first potential enum candidate, we just have a string that compares the variant name with the body string, and otherwise we crash. Does that make sense? I'm not sure. Let's construct a body here as well. And then let's do inner body equals That's pretty cool, right? So basically, by having this variable here, this, for every enum variant that we can possibly have, we kind of wrap that inner body in another switch that compares the strings and returns the enum if the variants match. Oh yeah, this does need the context. And then in the end, down here, we have basically this kind of nested switch, like this. Yeah. And now the only thing that's the kind of remaining to do is kind of append that body to the current body. Append that inner body to the current body. And that, I'm not sure how that works, but it should work similar to inlining in the optimization here. Hang on. Yeah, this one. Yeah, the inner body doesn't have any useful parameters. We just want to do this, basically. For every ID in the inner body, children, we don't even need a mapping, we just want to add that to the current body. Body.push ID or something like that. How does the yogurt builder look like again? I think there was this push. It has children. Oh, right. Yeah. Yeah, something like that. And whatever the inner body returns, that's what we are going to return. Cool. All right. Yeah, that does seem reasonable, I think. Let's compile that, see what happens. Oh no. Yeah, we need the type of that. So the type of this is the variant type dot value, I believe. Oh, this is a yogurt body. Oh yeah, true, this is supposed to be a yogurt body as well. So we need to create an inner body builder and have no payload there, and then kind of do that. All right. Oh yeah, that's a list. That's got a reference to that mutable list. That didn't change anything, which is not surprising because our example here doesn't contain an enum. That's totally fine. But we should be able to do this. Like if we import bool, and then here we have, I don't know, some true. Yeah, that compiles. Nice. Okay, so enums can be converted to a dynamic, but then also back to a static. To a static form. All right. What else? I think we'll need to. Arrays is still an open thing. Let's first commit that though. So in here, yeah, support. Yeah. Support converting enum to static, and then this is just some removing some to do. Same thing here. Yeah, sure. Remove some to-dos. Now, next, arrays. So for arrays, we have an array of dynamic values. And what we want to do is turn that back into an array of static values. All right, let's do that. Let's copy this one first and then adjust that. Okay, so this entire thing will be a switch. Because we need to switch on the dynamic value and only accept that if it's an array. Otherwise, we want to return an error. Dynamic to static failed, expected array. Beautiful. So given an array, we now want to kind of extract that kind of, you know, we know that the payload is an array. We now want to convert that to back to a static value. I think that's actually going to be similar to the other direction, to compile static to dynamic. Like here for arrays, we just took the length, we created a lambda, and then we generated an array that is basically that. Here we want to do something very similar. If we expect an array here, we want to get the, well, we know that the payload is an array, so we can get the length of that. And then we want to create a lambda that is, you know, a lambda that accepts a type int, and we need to know the type. That's like primitive, yeah, that's this one. Yeah, let's maybe grab that out there. Yeah, we want to build a lambda that accepts an index and returns an item. And the way that's going to work is using this compile dynamic to array items. Fun. Using the item type and the context. Alright, and the closure is going to be the original array. Yeah, and then we just generate the array of that length with the lambda, and that's going to be an array of the item type. And let's just use the type directly. And that is actually already what we are going to return here. Boom. So the only problem is implementing that function. So let's do that. And again, I'll make this heavily inspired by the other direction. So, yeah, we have enums, we have find a field, an array. Yeah, I don't know. Let's do compile array items to dynamic. Fun, yeah, but the other way around. Like compile dynamic to array items. Fun. Yeah, we get the item type and the context. All right. Ooh, yeah, then the signature will be converting dynamic to array item of that. Yeah, something like that. Here we have a tag with a body, and then we get the index, which, what the, no, that's not how that works. This is supposed to be an int. Let's fix that up there as well. Parameter, yeah, the index is of the int type, so libit type, I think. parameter type will be an array of items. Beautiful. Okay. Then, yeah, then in here, let's convert that to yield type to int. We are given an array of, well, dynamic items. And we want to convert those to static ones. So what we do is we get the array, first of all. We get the item, which is going to be a dynamic thing. And then we will convert that dynamic item back to a static one. And that's it, I think. Let's try to compile that, see what happens. Okay, that worked. Let's actually use that code. So let's create an array. For example, list of 1, 2, 3, and then converting that back to a list, and then getting the length, maybe. That works. Oh, that's crazy. Let's also see this one. So we call main 5. We create a list. I mean, fair enough, that's at some point that results in this one, I believe. That's, oh no, hang on, in this one. Yeah, that's the list. It's an array list, so it has an array and a length. And then we say toDynamic of that. Let's see where the indentation matches. Oh, here. Hang on. What's going on there? Dynamic to dynamic. Oh, I see. Here. So this is first of all a struct. And then it has fields. The first one has the name array, probably. Does array in ASCII. And the value is then, an actual array with integers inside. And then we have another field that's called length, value 3. And then we convert that back to a static thing. Nice. Nice, nice. So that means we want to convert that struct back to a static one. That means we're given this, we want to construct this struct with an array and a length. So we have these fields. And the first thing we do is we search for the array field. So we compare strings with increasing indices, the characters. Some field matches, and then we get the value out of that. Then we convert this kind of dynamic array of ints into a static array of ints by converting the individual items. Boom. Then we're trying to find the field, what is it, length, I think, in those fields. Yeah, the first field doesn't match. Fair enough. The second one does match. So the value of that int 3 is what we convert to an int. Clean, and then we format that. Alright. That's pretty cool. That is pretty cool. Now let's commit that. Was it support converting enum to static? And now we have support converting array to static. Nice. Yeah, the only kind of remaining thing that I might want to improve is, I mean, this is perfect. This is perfect. Types have no runtime information and you can't do anything with those. So, now what do we do for types? Actually not sure. I am actually not sure. Let's look at that. Okay, that doesn't exist. What do we do for the static to dynamic? Oh, I see. We have int, byte, and array, but types don't work. So let's say we have a type int, and we convert that to a dynamic and then back to a static type. And you can't do anything with a type, so let's just print hi afterwards. Yeah, unknown primitive type. I think we want to support that. So if the name is type, then we'll just create the variant type, which is this one. And it doesn't have any information because types don't have any runtime information. So it's enough to say, I don't even know. We can just say this is type like nothing, body.nothing has the value there. Yeah, that makes sense. And then also the other direction, converting something to a static one. Here we handle ints and bytes in the different order than above for some reason. I mean, well, sure. If we encounter a type, if we want to build a type from this enum, then I think we'll just do body.type of, I don't know, you could type never, maybe? It doesn't really matter what type we put there, because you can't inspect that. Here you can inspect types only if they are like statically known, like type literals. As soon as you can't construct types from some dynamic string or dynamic, something runtime known, and then you can't do anything with those types. The type info, the canonicalization, etc., that only works with type literals. So we can put any type that we want in here. You aren't able to observe that. And note, we don't need to recreate the exact type, as you can't inspect types. The runtime can inspect types. During runtime, they don't store anything. So we just give you any type. Mm-hmm. Mm-hmm. All right. So this should work. I am interested in the yogurt. What that's gonna print. It says to static. Mm-hmm. I of this. Add to dynamic with some type int. Sure, but that's just going to return the dynamic thing type, and then we convert that back to a type, and that results in the never type. I mean, sure. Actually, let's use the type. Doesn't really matter, but I think it's a bit easier to, you know, less confusing to see that there. All right, so types work. Let's see. Support converting types to static. Amazing. Well then, the only kind of weird or remaining thing, I think, is a lambdas. You cannot construct lambdas. I think that's kind of fine. Like, you shouldn't get the content of a lambda. You shouldn't like be able to reflect on the source code. And I mean, what would that even look like? You know, dynamic to static of some lambda bytecode, and then you get a lambda that you can execute, and that kind of requires doing JIT like loading that lambda content dynamically and whatever. No, that's weird. But I think we can store an actual lambda here. That accepts arguments and returns a return value. Oh damn. Because then you could build a function that basically sees that kind of constructs a new lambda by writing an actual lambda that accepts an array of dynamic values, and it builds up a return value. Yeah, something like that. Oh man, that's gonna be complicated. But I think it makes sense. Yeah. Yeah, that does make sense. Oh man. Mm-hmm. Oh wait, by the way, crazy that this doesn't Like throw an error or something? Sure. Lambda. Okay, so lambda's the big remaining feature here. Let's see, we have enums, we have lambdas, yeah. That should be possible, I believe. Also the other direction first. Yeah. So this is gonna be a lambda. But now I actually want to create a lambda that, you know, captures the actual lambda and wraps that in some sort of dynamic thing. Let's see how that works for arrays. So we have an array here. Yeah, okay. And here we create a lambda. The type of that is going to be a lambda that accepts an array of dynamic things and it returns a dynamic dynamic value. Compile dynamic lambda wrapper fun. I don't know. And that needs the actual lambda type now. Yeah, and it also captures the original lambda. And that lambda is then immediately kind of part of that. Oh man, that is mind-bending. Okay, compile dynamic lambda wrapper fun. Let's copy this function. Compile dynamic wrapper fun. Alright, that has a type. It's going to be the lambda type and a context. Yeah, this is going to be dynamic lambda wrapper of that. And then we have the, yeah, we don't have an index, instead this dynamic wrapper of lambda. It just accepts an array of the actual arguments. So it's going to have arguments, which is going to be, well, an array of dynamic ones. Yeah. Plus it's going to have a closure, true, of the actual lambda. Like so. Those are the parameters. Yeah. And then when that lambda is called, it gets the original lambda. And then that's like a static lambda, kind of typed. And what it does is it basically has to make sure that the length of the arguments matches the length of the lambda type arguments. So I think body.switch on some condition, that's going to be body.compare ins of the number of arguments. The number of arguments has to match the number of arguments in of that array, of the actual lambda. Okay, yeah, that's the condition, and then this will result in the lambda's return value. So type dot, this can be recursive, so we do need to type dot extend one level dot lambda dot unwrap dot return type. That's gonna be the result of this. Lambda type, let's actually store that, I guess. Yeah, then we can just do lambda type .args dot something and lambda type dot return type. Alright. And then we have less and equal. Yeah, basically if they are different, then that's an error, so we need to crash. Yeah, let's do something like that. Oops. Yeah, we want to build a body builder, we have the payload, and then we want to do body.finish with body.crash one number of arguments. Greater, well, same thing actually. If they are equal though, I think we can just, let's have like a top level switch in here. Make sure the number arguments is correct. Yeah. And this is not going to result in the return type. No, this is just the type nothing. Like so. Yeah, that makes sense. And then in here we can just say type nothing, something like that. And then if they are equal, everything's fine. We just don't need to do anything there. Alright. Oh yeah, payload type is not a thing. This is just type nothing, I believe. Alright. Alright. Slowly we're getting somewhere. Okay, we've checked that the number of arguments matches. And convert the arguments into static ones. Yeah. And basically the arguments, well, that's going to be a list of IDs, and then for every argument and the lambda type. We basically just want to do body dot call, oh hang on, like dynamic to static, yeah, of some value of body dot array get. This need to be enumerated. Array get of the array args. We want to get the argument at that index, and the type of that is going to be dynamic. And then we want to convert that to a static one, like so. And then, push that to this list, so that then we can actually call the function we can do body.call call lambda. We're just gonna have the captured lambda original. Oh, that's not even needed up there. I see. Let's move that downwards, I guess. Yeah, and here we get the original lambda, and we call that with the arguments, and that's gonna return, well, lambda type dot return type. And then we want to convert that back to a dynamic value and return that from our function. So we do body dot, yeah, this one, static to dynamic of that result. Yeah, something like that. And let's inline that maybe. Make things a bit clearer, like so. Clean. All right. Yeah. I mean, that makes sense, I believe. Array get needs just an ID, and args is a list of IDs. That's weird. Oh, I see. Yeah, static args. Sure. This doesn't need to be compiled. Makes sense, I believe. Yeah. Clean. Here, 190. This is, oh, I see, this is a reference to a type. Gotta do it like that. Alright. Yeah, converting those back to a static one is still not supported. Oh, that's interesting. Oh yeah, it returns lambda without anything. True. Two dynamic, static, two dynamic. I think the builder, the type builder more specifically, Let's move that like this. Builder and the types. Yeah, these need to be adjusted. Like these are fine, but here in the dynamic one, this is not type nothing. This is type lambda with, well, arguments, which are going to be the well, an array of recursive 3. 1, 2, 3. Yeah, that you know. And it's gonna return that, I believe. 1, 2. Yeah, another dynamic type. Yeah, then in here we have a struct with that doesn't really change anything, so yeah, recursive 3, let's double check that. 1, 2, 3, that's this, perfect. Yeah, fields. Oops. Let's do that like so. Clean. Clean, 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 clean. I like that. Alright. Cool. So now that type should match. I think I'm gonna make myself some tea. Okay, that worked. Let's maybe actually convert a lambda. So let's say we have some sort of lambda that takes an int and it returns that same int. Then we convert that to a dynamic one. Then we convert that to the static type, something like to foo. Then we can do lambda of 5, I don't know, dot font, that should print 5. Yeah, that's what I thought. Okay, there is no function named lambda in scope, hang on. Oh, yeah, that makes sense. Because we don't need these. Clean. Yeah, going the other direction doesn't, doesn't work. Dynamic to that. All right. Pretty cool. But apparently converting that works, which is quite dope. Let's see. So this results in a lambda with some lambda there. Now let's say the other direction. Oh, there's that. Let's see. What's called dynamic? The other kind of dynamic. This one. I'm converting a lambda to, to a static one. Dynamic lambda wrapper fun. Oh, you know what? Let's actually copy this case right here and copy that down here. Yeah, try to create lambda from dynamic. I suppose that's the error that we get. It's maybe, oops, well, was that some personal stuff? I don't even know. Not really. And I wanted to check this error message. Oops, just copy that, paste that in here. Yeah, try to create lambda from dynamic. That's the error that we get. Let's do that. Let's say we put something, well, not that. We take only this part, insert that down here. Alright, so we want to create a lambda of the type, you know, the type that we want to compile to, the static type, which is going to be a lambda type. And the lambda is going to be compiled static lambda wrapper fun of that type. And it captures the value, which is going to be, oh, that doesn't exist yet. Yeah, I see, we need this sort of switch that, because of course we do, and that switches on the dynamic value. Yeah, if the name is lambda, oops, then we want to do that. Yeah, then we want to do body.lambda of that type, compiling a static lambda wrapper fun. Capturing the payload of that lambda, which is going to be the actual lambda. So now let's compile that static lambda wrapper, which will be simpler than the dynamic one, I think. Maybe? I'm actually not quite sure. Yeah, we have array stuff, we have find field and array, boom, and string comparison. Sure. And then at some point, boom, we're gonna have the static lambda. Static lambda wrapper fun. That's gonna be a lambda. We know that's a lambda, so we can do this. I don't know. And then we'll have the arguments. So we create a lambda that takes the arguments of those types. So clean. Alright, for every argument we add a parameter to the body of that argument type, and then we also have a closure, which is gonna be a dynamic lambda kind of thing, you know. Why is that not yet a type? Type dynamic lambda, and that's basically gonna be that, except only this part. So a lambda type, and then we need to insert the type, I don't know, type info lambda, that's fine. Type dynamic. Oh, yeah, an array of types. And it's gonna also return a type. Yeah, only a tiny bit simpler, because in here we can say type, instead of type lambda, we can say type recursive of 3, possibly. Let's see. 1, 2, 3. Yeah, that's the lambda. Alright, and for these, maybe we can also simplify stuff. Recursive of 2 would be 1, 2, but that is wrapped in an array, so we can also do that. Here, recursive of 3 with 1, 2, 3, that makes sense. 1, 2, that also makes sense. Alright. And then the return value is just gonna be that, although the lambda again can be simpler. Recursive 2, I believe. Let's see, 1 would be here, 2 would be that one. Yeah. And in here that's 2 because there's 1, 2. Yeah, that seems fine. Alright, so that's something. We have type dynamic lambda, which we can now use in here, because we know that this closure and this parameter is going to be a closure that captures a dynamic lambda. Yeah. And we are currently building a static wrapper for that. So here we have a lambda, and we have the lambda type, we have the arguments, which are parameters, and then we have the closure parameters. Okay. Now we want to turn the arguments into dynamic arguments. You want dynamic args, yeah, something like that. And then for every argument in the args, we basically want to do body dot static to dynamic of the corresponding type, which we need to get here as well. So we also need to iterate over the lambda type args, like so. And then here we can do arg dot a, which is the ID. The type is going to be arg dot b, and then context, I believe. And then we can do dynamic args dot push that. Clean. Then we have converted the arguments into dynamic values. Next we want to put them in an array. So body dot array of dynamic args, like that. This doesn't work because this it doesn't make any sense. What's going on here? This needs a type. Oh yeah, and this is probably the entire type of the array, which is going to be type dynamic, I don't even know, trapped in an array. That can probably be simplified. I assume that's not totally canonicalized. I'm not sure. Okay. Oh, then we have an array of dynamic ones. Now we can actually call the original lambda. So we can do body dot get closure. After closure, that's going to be a lambda, and then we can call body call lambda, that one, with, well, just a single argument actually, and the dynamic args, which is going to be an ID, makes sense, and that's going to return a type dynamic. Okay, makes sense. And that's the return value, or the results. And then we can do body dot dynamic to static of that result to convert that back to a static type. Of course, that needs the type that we want from that. So this needs the result and the lambda type return type, and possibly also the context, like so, boom, boom. Oh yeah, that was called converted. That's actually a good name, I believe. And then we are done, and we can kind of return that static one. Okay, this call doesn't work because this needs a type true. That closure is of the type, this one, type dynamic lambda. Okay, I mean that's crazy. Okay, what we do is we convert a lambda to a dynamic lambda, and then we call toStatic on that to convert that back into a lambda from int to int. So we call dynamic to lambda from int to int, and this is the dynamic, it's a lambda. And then here we have a dynamic lambda wrapper of something, and we call the dynamic lambda wrapper. That's weird. No, we want to call the, what's it called, dynamic lambda wrapper? Should be called static. I see. And that means that wasn't compiled because that function already existed, and that stuff was weird. All right. Static lambda wrapper. That works. Amazing. Okay, let's actually look at that, because this is quite this is crazy. We call toDynamic on that lambda, resulting in a lambda with a dynamic lambda. Dynamic means this lambda will accept an array of dynamics and return a dynamic. Then we convert that back to a static, which just returns a lambda that is the static lambda wrapper of that. And when you then call that resulting lambda with a 5 here, for example, and the closure capturing the original lambda, the dynamic lambda, and what we do is we actually convert that 5 to a dynamic value like that. And then we put that in an array and call the dynamic lambda wrapper. With that, and that captures the original static lambda. So this then converts that back to a 5, calls the actual lambda, the identity function in our case. Something just flew in my flat. Well. And then that turns the return value back into a dynamic one, returns that, and then the surrounding static wrapper turns that dynamic thing back into an actual 5. That's crazy. That is crazy. Okay. Support converting lambdas to dynamic and static. That's crazy. That is honestly... that's cool. Yeah. I mean, this is pretty nice. You can now take any value, including bytes, integers, arrays, structs, enums, lambdas, and even types. Like weird recursive value, literally any value in Plum. You can call toDynamic on that, and you get back this dynamic representation that is a first class, the representation of the structure of the value. So if this is a struct, you can literally iterate over the fields and see their values. If this is a lambda, then you get an actual lambda that accepts an array of arguments. That's crazy. And then you can, not only that, but you can turn that back into a static type if you know what type that was supposed to be. That is crazy. What? Cool. Yeah, I'm happy. This is quite cool. And I think in the next videos I'll probably play around with that and use that to implement some useful functions. For example, we already have formatting arbitrary values. Maybe even writing a generic hash function that can hash any value. Or doing some formatting stuff maybe. Or, I don't even know. Having a function, something like what we call kind of like any foo. A function that accepts a type and then returns you an instance of that type. Any instance. Or even like a, like random, give me a random instance of that type. We could build something like that. Or maybe even, passing JSON and then converting that to a known expected type. Yeah, that's gonna be fun. So that's it for this video, and I guess see you in the next one.